Okay, guys, so today I don't have my black marker, but have another 3 colors, so we should be okay. So this is dynamics. Today is 2:15, and this will be lecture 10. Perfect. And for me, that will be page 58 on the class notes. Okay, so like I just said a few minutes ago, today I don't have any intention to move ahead on the class material, but maybe to try to work with you some other problems, some practice problems, or answer any question you might have about the homework. So whatever you want to do, guys. So I think somebody had a question about problem, what was it, 278? 378?
Oh, 273.
273, okay. 273 out of the homework. So let's see what is 273. So let me open this. Alright, so 273. There we go. Okay, so let's see. So figure 273 shows a gas containing a vertical piston cylinder assembly, a vertical shaft whose cross-sectional area is 0.8 is attached to the top of the piston. The total mass of the piston is 25 kilograms. While the gas is slowly heated, the internal energy of the gas increases by 0.1. The potential energy of the piston combination increases by 0.2. And a force 1334 is exerted on the shaft in the figure. Okay, so what's the question here about this force?
Actually, like answer A, you have to find the work done by the shaft, right? So how can I find the mass of the shaft itself, not piston plus shaft? Is 25.
So the piston and cylinder are poor conductor and friction between them is negligible. Okay, the local atmospheric pressure is 1. Determine the work done by the shaft. Why do you need the mass of the shaft? How do you find the work? What is the definition of work?
PD is mgh.
What is the definition of work?
Work is the force and distance.
Force times distance. So do you know what is the force? So you need to find out how much, I don't know if they tell you, but how much is this going to move, no?
And then in order to find
So why do you need the mass?
in order to find the distance, I was looking at the P, the potential energy is same as the mgh, so I was trying to find h, but then I just need the mass for the shaft, not the piston and the shaft.
Okay, so I see. So you're trying to find out the h, no?
Yes, sir.
Let's go to here. So this is 0.1 kilojoules. Okay, so this is the potential energy of the piston combination increases by 0.2. This one and the force on the shaft. So basically what I'm trying to do is mgh will be equal to this 0.2. Is that what it's doing?
Yeah.
So we're trying to find the h. And what they have here 25 kilograms.
But then that 25 kilograms plus piston.
Okay,
plus
but they tell you the total mass of the piston and shaft is 25 kilograms. So Right, the mass is given to you, no?
Yeah, I know, but I was looking for the, if I just use the mass of the chef only, or just together.
I mean, what is the work? Is the work only going to be done by this little thing over here? Or is going to be done by the whole thing?
Working.
No? What you're telling me is that what you were looking for is just for the mass of that little pin over there, no? But you don't need that one. What you need is the air. What's doing the work is what is. If you move this is going to move, no? Okay. There is no way to move this without moving this. So the mass is being given to you.
Well, that's why the wording's out. Because yeah, it says work done by the shaft. You're saying that that's why, like it's understood the piston's moving with the shaft because it's actually connected.
I'm not. Yeah. What do you call the piston? This?
Yeah.
Yes. Yes. Yeah, it's strange that they ask you the work done by the shaft, the work done by displacing the atmosphere. So basically what they're asking you, I think, is the work done by this, the force plus the weight of this, okay? How much is this? And then what is the work done by the gas inside? If you do like a little figure here with arrows up, no? What is the work done by the gas inside? Yeah, I agree with you, it's a bit confusing the way they ask the stuff. Okay, you have more questions? If not, what we can do is very simple. I can just go and pick a problem out of chapter 3. I'll give you about 15 minutes to do it, and then we can do it together. And in the meantime, you can ask me questions. You want to do that? Since you don't have questions? So I don't know if is 336 part of the homework? Oh, it's
35, no? 36?
somebody asked me about 35. Let's see what 36 is. Is that one part of the homework?
No.
So what about, guys, you work on 336? I'm gonna have to do it smaller, this, so you can see the figure. Can you read or no? Probably not, no? So what about you do that figure very quick, and then I'll put the problem statement. Draw that figure. Okay, well, I can do it with you. Hold on 1 second. I can do this one, maybe I can do this. Okay, so let's say, so as practice problem, I'm going to do problem 336. So before looking at the problem statement, looks like we have a piston cylinder assembly. Okay, so the atmospheric pressure is 1 bar. We know the substance is refrigerant 134A. There is heat being applied. And then what do we know? Looks like the weights of the piston is 471.1 newtons, and the diameter is 0.02 meters. Okay? They tell you that initially, so let's say state 1, this is saturated vapor. And what do we know about state 2? The temperature is 160 degrees Celsius. Okay, so now let me go back to the problem statement, see if we can get any additional information. Whoa, I don't know what I did. Oh, I moved this one instead of the page. Well, let me stay here, page down to 336. Okay, so as shown in figure 336, refrigerant 134A is containing pistons in the assembly initially at saturated vapor. The refrigerant is slowly heated until its temperature is 160 degrees Celsius. During the process, the piston moves smoothly in the cylinder. For the refrigerant, evaluate the work in kilojoules kilograms. So what we need to find is what? We need to find work per unit mass, which will be kilojoules per kilogram, no? All right? So, in every single problem, some problems is more needed than in other ones, but what is something you always need to do? Draw a figure, no? So you always have the choice between what? PV or TV. So which one you want to do? It's a piston. So generally, what is better? What is going to be constant in the piston? Pressure. So sometimes it's better to do the TV, no? But you can do the other one. It's not a big deal at all. Okay, so let's say we don't know the pressure, but we can say within the pistons in the assembly is going to be constant pressure. Okay, so what do we know? What is the initial state? Saturated vapor. So that would be what would be that point? Here, no? Yeah? Okay? So do you have any question about, do you understand what needs to be done in this problem? So basically, every time you do a problem, in order to go at the tables, you need to know two things. So over here, do we know can you know the pressure inside? You can find it. Basically, the pressure here will have to sustain what? The weight of the piston, no? Or the weight of the piston will be equal to the value of the pressure inside. So once you have the value of the pressure inside, you will know what is the value of P, no? You can go to the tables, you can find what is Vg, what will be V1. All right? So go ahead. I'll give you, it's 11:34, so let's say it's 11:35. I'll give you until 11:50. You have a question?
When we find the pressure of the piston, do we include the 1 bar of atmospheric pressure as well? So
Yes.
we find the
Yes, so that would be, do they give you the weight of the piston or just the force? They give you the weight, the 471.
So we can find the pressure, because it's just force over the area. Would we find the force over the area plus the 1 bar of ATM?
Yeah, initially my answer to you would be yes, since they
Okay.
put the pressure over there.
Okay.
Okay?
Thank you.
Yep. So go ahead. Since we don't have that empty time on the recording, I'm just going to put a pause over here. Okay? So I'll give you 15 minutes to work on it, and then we come back and do it together. Okay. So let's see. So we know this is saturated vapor. Okay, so what else do we know is that since this is happening in a piston cylinder assembly, what's going to happen? We know that P1 will be equal to P2, no? Okay, so now maybe I'm going to go to the next page, but always keep this figure. So let me just take now, I don't have a black, I don't have another marker, just this one I think is too thin, no? To write with it. So, okay, if I do just the piston here, I can do everything probably. Okay, so if I do the piston, again, I need figures in order to solve the problem. Don't think that I know the solution right away. So just like you, I need to go through a process. But the pressure inside should be equal, should do what? Should be the one resisting. So this is, if you want, the force inside will be equal to pressure inside times the area, no? Yeah? And that force over here should resist what? Should resist the weight of the piston plus what? Plus the force created by the atmosphere, that will be equal to what? P atmosphere of 1 bar times the area, no? Because you know that, what? You know that pressure equal to force over area. So that force is going to be pressure times area. Yeah, I think this is too thin for this, so I won't use it anymore. Okay, so now we go back to what? I mean, we could say for equilibrium, but if you want to think about another class, this becomes what type of problem? Static problem, no? So measurable forces on the vertical directions need to be equal to 0. So if you look at it, this will give you what? F, or yes, so if you want, will be force inside, so, or if you want, minus F atmosphere minus W plus P times A needs to be equal to 0. Or just rewriting this, what do we have? We have P times A will be equal to what? P atmosphere times A plus the weight. All right? Or P will be equal to what? P atmosphere plus the weight divided by the area. So, in this equation, where P atmosphere is 1 bar, do we need to change those units? I mean, probably yes, because we want to deal with what will be the normal units for pressure. Pascals. So 1 bar is how many pascals? I think, but okay, but let's work on kilopascals. I'm guessing, or 1 pascals will be 10 to the 5th. It's 100 kilopascals, but let's say it's 10 to the 5th pascals, no? I don't know what would be easier for the units. Okay, now, what would be A? What do we know about, what do they give us in the problem? The diameter of the piston is 0.02 meters. So what would be then the area? By, if you do this one square instead of the radius, what are you going to have? Divided by 4, no? So, okay. And W is equal to, and the weight is equal to what? 471.1 newtons. And you know that 1 Pascal is 1 Newton. Oops. per meter squared. So P here, this P is really equal to what? P1 and P2, no? So if you do the calculation, I'll let you do it. What do you get? 16 bars. So then it's 16, so
600 no, 600 kilopascals.
so okay, give it to me in bars and then in kilopascals, and then we move it to bars. So it will be 1,600 kilopascals, which is 16 bar. Okay, I'll let you do the calculations. You see that I'm not the one doing the calculation. So it should be page 59. Okay, guys, so you see, always do a figure before getting any equation, no? All right? So any questions so far? Okay, so now that I know the pressure, what can I do? I know that this pressure will be what over here? 16 bar, no? So now for the substance, refrigerant 134A, can I go to the tables and look at the 16 bar? So let's see, what will be that table? So 24?
944.
Okay. So I go over here, I'm gonna have to maximize this. So this is SI units, so
It's probably not gonna come up exactly as 944 like the PDF.
oh, you say the page, yeah.
Yeah, they're a little bit off.
So, but it's table. Would you know the number of the table? 11. Okay. So the refrigerant L34 here.
That's the English unit.
Oh, this is English unit, so I need to up. All right, but I know it's 11. Sorry for that. There we go. No. Almost there. 11. So looks they give us the pressure in bars, which is good. So it's 16. So we go down, and at 16. Okay, so if we wanted the temperature at 16, what do we know over here? So we need to know the V. So we know V will be equal to Vg, no? Yeah? So from table, so we can write down over here. So let's see. From table, A13, A11, sorry, A11. So at A11 at P equals 16 bar, what do we know? V1 will be equal to Vg, which is equal to 0.0121 cubic meters per kilogram. Yeah? Okay. Also from the table, what do we know is the saturation temperature at that pressure? What is the temperature? 57.92 Celsius. So if I come to this figure, I know over here is 57.92. Why am I doing this? Because now What do we know about the temperature at state 2? Is 160, no? So from the figure, we know that state 2 will be where? Will be along the line of constant pressure, no? So we'll be along this line. And where will be V2? V2 will be over there, no? So in order to use the tables, we always need to know two things. So in this case, we know the pressure, and what else do we know? The temperature, okay? So now we know from the figure that we can go probably to table, I don't know. So from table A, yeah, I trust you. I don't know the table. So A12 will be the superheated. So A12, we go at the one that is 16 bars. From table A12 at P equals 16 bars and T equal 160. Do you have 160 or do you have to interpolate? Good. Oh, you have it. You are lucky, huh? Yeah. So basically, you also find here the saturation temperature to be 57.92. V2 is, which value on these columns is the first one. So we go 16, 160 over here. What is the value for V2? 0.02017. So we find that V2 equal to 0.02017 cubic meters per kilogram. Okay, so now, I mean, you don't need to do this, but if you needed to find the work graphically will be equal to what? The area between those 2 points, no? So what do we know about the pressure? It's constant. So what is the work done by the pressure when it's constant? It's work equal to minus P dV. I'm going to start going a lot faster now. So that means what? That work over mass equal to what? Minus P dV, but the V specific volume, no? Okay, I've done it like 3-4 times already. All right, because specific volume is volume divided by mass. All right, so from here for P equal to a constant, work over M would be equal to what? Minus P V2 minus V1, no? After integration. V1 I can put here. Okay, so you know P is equal to 16 bars, so it's going to be equal to 1600 kilopascals minus this, so that should give you the result in kilojoules, no? So if you do these calculations, what do you get? So kilojoules per kilogram. Is that correct? Negative 12.9? Okay. So again, it's I don't know about the value, but does it make sense that the value is negative? Yes, because it's moving basically up because you add heat, so it's creating work, no? Yeah, it's work done by the piston, being negative. So you see, when I'm the one doing it, everybody understands. Okay? Doesn't look that difficult, but when you need to do it, it's like the free shot in basketball, okay? Any question about this problem? Is it clear? All right, so let's see if we have time to do another one. So, chapter 3. Okay, I don't know. Let's go on the 50s now. I don't know. I don't see figure. No, this one. No. I mean, this one is probably. Is 371 part of the homework?
Yes, sir.
Okay, so before we move to another one, I have no idea what this problem is asking, but just by looking at the figure. Okay? I'm guessing here you're going to have two things happening. So what's going to happen between this position here and the position here where you have this type of locks over there? This process will be constant pressure, no? But then once it hits over here, it's not going to be constant pressure anymore, no? Yeah? Okay, so I don't know what it is about, but just want to mention that about that figure. So I don't know, let's do. Okay, so let's say, is 374 part of the homework?
No.
Okay, so go and do 374. Can you read it, or do I need to do it bigger here? So I'm going to pause this, and then we'll go back. I'll give you about 15 minutes to do it, and then we'll try to finish it up. Or I'll give you just the main lines in order to finish it. Resume. Okay, so let me just go back for a second. So guys, I forgot to resume the video, but I'm gonna explain it very quick. So basically we're doing 374. I do the TV diagram. We know process 1 is saturated vapor, so we are at this point over here. Okay? Then the system is cooling down to what? To a mixture of 75%. So we know pressure is constant, so it's going to move left along this line. So process 2 is right over here. Okay? And we know the mixture will be 75%. So X2 will be 75%. Then process 2, 3, we know V2 equal to V3. So we are over here, V2 equal to V3. And this time we are heating. Again, this is a heating process, and we heat it until we go back to state 3, which is 100%, which means 100% gas, no? So we need to go back again to this point over here. All right? So first thing we are doing is to calculate what is the work between state 1 and state 2. So for the process 1, 2. So we know that process is constant pressure because it's along the line. So the work done by a constant pressure process is minus PdV. P is constant. You move the V outside, so it will be minus P, V final minus V initial. Okay, but since we have the mass, this will be minus M times P, V2 minus V1. Okay? Okay, I'm guessing that we're going to have to move this one to square foot, okay? But we can do that for me. So what would be V1? So in order to find V1, we need to go to the table. So I'll let you finish it. We go to the table. So what will be the tables we need to go? Table A14, okay? A14E at P equals 100. So let's do that very quick. We can go there. No, let me just. So you go to this table, and you're going to find that V1 will be equal to what? From the figure, V1 is equal to Vg. Okay? Whatever that value is. Okay, I'll let you finish it on your own. Now, we need to find V2. Okay? From the figure. Alright? So, also from the figure from table A14E, you're going to find V1 equal to Vg. So this will be for V1. For V2, what do you know about V2? V2 will be equal to what? So also you will go to table A14E at P equals 100. But now, what type of information do you need? V2 will be equal to what? Vf plus x2 Vg minus V fluid, no? And the V gas here is the same as this one, but you need to use the V fluid, and the x2 over here is 0.75. Okay? So now you find, so now using V1 and V2, so we have here V2 equal. Okay? You can solve for work 1, 2 will be equal to minus m times P V2 minus V1, and you're going to have to do some unit transformations from foot-pound force to BTUs, no? Okay? And here you're going to get the results into BTUs. Okay, let me close this. All right, so now we find work 1, 2. We also need to find what? Q1, 2, no? Okay, so in order to find Q1, 2, what do? Apply the first principle of thermodynamics for 1, 2, for process 1, 2, we give you what? Q1, 2 plus work 1, 2 equals to what after neglecting kinetic and potential energy? Change in internal energy. Okay? So we'll have Q1, 2 will be equal to M U2 minus U1 minus work 1, 2. All right. So now in these problems where M is equal to what? 1.2. Now U1 will be equal to what? We need to go back to the figure. So what will be U1? U will be UG from equals to whatever it is, table A14, no? A14E. At 100, the same thing you had, V1 equal V sub G, you're going to have U1 equal to U sub G. The same table. Okay? Now, U2 will be equal to what? Correct. And again, this will be from the table A14E. Okay, so now you can go and substitute into the equation, and you find this in BTUs. Okay. Now, okay, now for process 2-3. Okay, and I know they don't ask it, but we know V2 equals to V3. So if we do the work 2-3, what does that mean? Work 2-3 is 0. Yeah? Okay. Now, we apply first principle. Of thermodynamics for process 2-3. So we're going to have Q 2-3 plus work 2-3 will be equal to the change in internal energy 2-3. So we know the work is 0, so that the change in heat will be equal to the change in internal energy. So where M is the 1.2, the U2 we found it before, no? Okay? And now what about U3? So what do you know about U3? So basically here, guys, what I think you need to do is this, okay? In order to find U3. So U3, you know, is saturated vapor, no? Okay? So, what else do you know? You know that V3 will be equals to V2, and that it will be saturated vapor. Okay? So what you need to do is go to the tables. What were the tables? A14. So you can go, I don't know to which one, but let's see. Probably go use A15, but let's say you use A14. Okay, you know what will be V2, no? So you can go over here and see what will be the value of V2, the closest one. So if we had, what was the pressure here? 100. So I'm guessing it's probably going to be higher than 100, no? So what is the value of V2? Do you remember what was the value for V2? Well, once you calculate it, you see you come to this table, A14E, and you interpolate, no? So you find the P, and then you can also do the same thing. You can interpolate. So U3 will be equal, so go to table A14E and interpolate to find U3. Do you kind of follow the process? But again, it's because I'm doing it. If you do it, I tell you, you need to practice, no? All right, so it's 12:30. So guys, practice. Homework due on Tuesday, no? So come with questions on Tuesday.